Okay, so welcome to the day 4 of our lecture series. So let me first recall what we have learned in the. So let me check if it is. Yeah. So let me first briefly recall what we have learned in the first three lecture series. So we have learned about data. So what we have learned. Okay. So first we have learned about data or so variable types. Then we have learned about matrices, arrays, and their operations. Then we have learned about conditional statement, how to implement them. Then we have learned about loops. So this is for iterative tasks. Then we have learned about basic plotting in MATLAB. So in plotting, we have learned about 2D line, 2D plot, 2D plot. So there we have explored line plot, bar plot, scatter plot, and in 3D plot, and then we proceed to 3D plot, and there we have looked at what I mean in 3D, what is a line plot, what is a surface plot, how we can do the mesh plot, and there is also contour plot. And then we have learned about how to define a local function of your own. So define function in MATLAB. And there also you have learned about how to, how to, there also you have learned that you can call a function inside another function. So, nested function kind of thing. So that we have also learned. So now today, first we will learn about, so today's lecture. So the first thing what we will learn is, so we will learn interpolation. So let me introduce you to the idea of interpolation. So what is this interpolation? So I have talked about this earlier also in lectures. So for example, when we have this, this data set. So if you are plotting something, so you have some particular data set and you are connecting a line. So so the line can be, it can be do from the standard deviation also. And so and suppose you want to know what is value along of this dependent parameter for for an intermediate value which is not present in the data set. So idea is this. So if we have a data set, so for example you have an array. So suppose this is from x equal to, so this is your array, and suppose you are having a y value corresponding to it. So it will, you have to write it in this way. So if you plot it, so here you will get the corresponding value. So for x equal to 1 you will have y value to be 1, for 2 you will have some another value, for 3 you will have a value, and in this manner, so you will get a plot. So this is how your data will look like, and so these are your point from your data set. So so you can uh, define a function from which you will get the data set, or so you can collect the data from the experiment. So when you are doing experiment, so you don't know what is your model. So that model can be so there can be lot of parameters which you don't know about yet. And so in experiment, so from when you are getting data, and suppose you want to know what is the value for an intermediate value of this independent parameter. So for example, you are calculating the you are recording the displacement of your oscillator with time. So you are calculating the displacement of your for example, you are taking the snapshot, and from image analysis you are looking at the displacement from the center position. So suppose you are taking pictures in 2 second interval, so your data time set will look like this: 0, 2, 4, 6, 8, 10. So this is how your time series data will look like. And for this time, so from the snapshot and from the image analysis, so you are looking at the displacement from the center position. So I mean, you will have a corresponding y value. So this is y0, this is y2, maybe y4, y6, y8, y10. So this is how your data set look like. Now suppose you want to know what is the displacement from the center position at an intermediate time. So for example, you want to know at time t equal to 1. So that is not present in your data set, and when you are dealing with with an actual experimental setup, so you don't know precisely what the model is. So I mean, you can consider just linear oscillator model, but maybe your system is a damped oscillator, so it can be present in presence of thermal noise and so on. So you don't know what the precise model of your system is, but you want to know what is the x value. You want to know, estimate what is the best possible x value, best possible displacement value for an intermediate time. So for that, you have to know how interpolation works. So basically, there are lots of ways to do interpolation. So the simplest possible way is, I mean, so looking at the nearest data. So how it will work here? So here, for example, suppose you want to know at this x value. So this is your, suppose, xm, where you want to know what is the interpolated value. So the simplest case is, I mean, you just look for x point which is nearest, and assign that y value. So for example, so when you want to calculate for x equal to xm, so if this point is your neighbor, is your nearest, so I mean, this y value you will assign it here. But you can see that this is, I mean, this is not a good approximation. So because at this point, so you are obviously taking the same value. So this is the simplest kind of interpolation, and that is why it is not very effective. So that is why the simplest kind of interpolation, which is nearest neighbor interpolation, so that is not used often. And the next thing what you can do, so you can do the linear interpolation. So what is this linear interpolation? So now, instead of just assigning the value of this nearest neighbor, you look in both directions. So you try to find in this direction which is your nearest neighbor point, and also you trying to find in this direction which is your nearest neighbor point. So once you get these 2 points, then what you can do, you can connect a straight line between these 2 points. So and I mean, if you know two points, then you can write down the equation of the straight line. And if you put the x value, so I mean, you will get the equation of the straight line, and by putting the x value you will get what is the corresponding y value for linear interpolation. So this linear interpolation, I mean, so this almost give you the correct value if you have a large number of data points. So in this range, so for example, if you in this range, if instead of this 5 point, you have 500 point, in that case, the linear interpolation almost give you exactly the same value. So let me show you how you can extract this, how to do this strategically. So for example, this is your 1 point, and so you have this. These are your data points, and this. So let me okay. So this is your axis. So here you have one data point. Here you have one data point. Here you have one data point. Here you have another data point. Now you want to find for this. So suppose this is your xm. So this is not present in the actual data. So these are your actual data. This you have this four data point, and you want to know what is the value for this x. So at this point you want to know what is the y value. So it can be this, it can be here, it can be here. I mean, if you do the nearest neighbor, so obviously the value is this from the nearest neighbor, because I mean, if this is the nearest one, then its value will be y value will be this, and if this is the nearest one, nearest point, so the value will be here. And the in linear interpolation, what you will do? So I mean, you have to write. So if you want to write it from scratch, you want to build your own function. Then what you can do? So first you will search in this direction, which is your nearest point. So this is your nearest point. So suppose this is x1 y1. Then you will search in the opposite direction, and here this will be your nearest point. So this is x2 y2. And once you get these 2 points, so I mean, you can easily write down the equation of the straight line. And so if you have 2 points, then what is the equation of straight line? So we know that it will be x minus x1, we can write this way. So y minus y1 divided by y2 minus y1, and here we will have x minus x1 divided by x2 minus x1. So from that you can calculate what will be y. So this will be y2 minus y1 by x2 minus x1 multiplied with x minus x1 plus y1. So this is how your equation of the straight line connecting these 2 points. So this straight line equation will be, from this will be a straight line equation. So now if you put x equal to xm, then you will get what is the y equal to what is the y value. So for x equal to xm, you will get the corresponding y value. So this is how the linear interpolation works. So MATLAB has an inbuilt function for this linear interpolation, and so let me show you in MATLAB how you can use how to do this interpolation. Okay, so let me open a new space. Just close all of them. And let me just save it with the name. So the so I will write out. I will show you how MATLAB works with this linear interpolation function. So this is a name. So what is the process? So you have, so first you will have the an array for your x-axis. So let me call this an x array, and suppose this is from 1 to, I mean, so gap is 0.5, and then you will have 10. So this is your x array. And for example, suppose you have y values. So y array. So I mean, let me write down a function. So it can be x squared minus 2 sine x array. Okay, so this will be X array. Okay, so if I run this, so I should have these two arrays. Okay, so you can see that this is our X value is 1, 1.52 and so on, and for each of these X value we have this Y values. Now what do you want to do? So what do you want to do? So you I mean we want to know what is the, so let me define as xm. So I want to know what is the y value for this x value, and this is not present in the data set. So for example 5.25. So if you look at the x array, so you can see that there is 5 and there is 5.5. So there is no 5.25, and I mean you want to know what is the y value. So and there is a inbuilt command in MATLAB. So ym, so ym, and so for, so the inbuilt function is this interp1. So this is for interpolation, and then first you have to write what is your x value, which is the independent parameter. So for my case this is x array. So this is my independent parameter value. Then I have to give the give what is the y array for this. So for each of these x point, what is our corresponding y value or the dependent parameter value. So that is our y array. And now then you have to write what is the data point where you want to interpolate. So for example you want to interpolate at xm. So at x equal to xm you want to know what is the interpolated value. And then what you will do, you have to specify the method. I mean there is this nearest which I was talking about, and there are other methods also. So right now I mean we will look at the linear one. So let, so you have to write down here linear. So if I run it, then you can see that this is the interpolated value. And if I have the nearest one, so let me check with that. So let me look at the output. Okay, so it is 31.66, and let me look at the y array. And also look at the x array. So 5.25. So that means so let me specify this as 5.3. Yeah. So so the point 10, it seems to be the closest. So what is the y value for point 10? So it is 31.6611. So you can see that it has straight away assigned that value to the interpolated one. Now instead of nearest, if I write down here linear, so if I want the linear interpolation to work, then you can see that the value is now different, and it is in between these 2 points. So it has fit a linear uh, line between the 2 points, and from that it has calculated that. Now we can try to write down the logic by which the linear interpolation works. So so what is the process? So first we have to look for the x point which is closest to that. So how you can do that? So you want to so for that what you can do, so here you have your data point. So for example x this is your x value 3, 4, 5 up to 10, and suppose you want to know at 3.3 what is the interpolated value. Then what you can do, you can check what is the difference between the number between the elements of the array and that actual number. So you can, whenever the difference is less than 0, so I mean that will give you the set for in one direction, and whenever the difference is greater than 0, so that will give you the set in the other direction. So you can store them as two different you can store them in two different array, and from each of the array, so if you extract the end element here and the first element from this array, then you will know what are the x points from your data set. So for 3.3 it will be this 3 and 4, so you can extract from that. And you can so there is an inbuilt command in MATLAB from which you can find the index corresponding to that element. So if you write down that, so it will tell you that it is at fourth position. So then what you will do, so if you know what is the position of the x, then simply you can extract that element of y by writing this. So in this way you can extract what is your x1 y1 and x2 y2. So once you are done with your x1 y1 and x2 y2, then you can, and this is your xm, then you can easily calculate what is the y value at x equal to xm, and we can check with the MATLAB inbuilt function, so if our program is right or not. So let me do that. So what do you want to do? First I want to store. So let me write down the variable as smaller. So what it will check, so it will so in x array I want to know the elements where this xm minus x array, so that is greater than 0. Now let me run it. So what should be the output? So xm minus x array greater than 0, that means the element from 0 to 5 that should be stored in the smaller. You can see that this is the array. So as long as this condition is being satisfied, so all the elements of x which are satisfying this condition, so first it will take the first element, so which is 1, and it will check this if xm minus x array greater than 0. If it is the case, it will store it in the smaller. So in that way you can store all the values that are less than our desired x. And in the similar fashion, you can look for the larger element, so larger, and you can write x array. So you have to write down here just the opposite. So now it should be greater, it should be less than 0. So it should store from 5.5 to 10. So you can run it. So now you can see that this is a smaller array, this is a larger array. You can change it. So if I make it step size, for example 1, and let me change the point, for example 7.3. Now you can see that these are the numbers in the x array which is greater than xm, and these are the numbers in the x array which is smaller than the xm. So in that way you can store them individually. Now you want to find the index. So now what you want to do? You want to extract this last element from the smaller array and the first element from the larger array. So I will write down x1, which is the last element of the smaller. So for to extract the last element, we have to write down the n. Should it give me the index? Okay, maybe not in this way. Let me check something if that works in MATLAB or not. Okay, so there is no, we cannot do in this way, so you have to find other way. Okay, so x1 smaller n, if I write down this and if I run it, so you can see that this is the x value, which is this is nearest neighbor, one nearest neighbor point. Similarly, x2 I can get from the larger array, and that should be the first element. So if I run it now, you can see that this the points we have gotten. So let me show you that this works for a different number. So let me give 2.2, and it should give me numbers 2 and 3. So you can see that this is our x1 point and this is our x3. So for this x1, if I want to know what is the y value, so first I have to find out the index. So what is the index of this element in our original x? So I mean, so the in so if I make it 0.5. Okay, so this is our x array, and we want to know what is the value for 2 equal to 2. So I mean, the x1 point should be 2 and x2 should be 2.5. So which is fine. Now you have to find out the index. So I mean, you have to know what is the, you have to tell some way to MATLAB that what is the y value for this position. So you should extract y13. So what is our y array, and you should extract these 2 points. So how do you tell MATLAB that you should get the third element and fourth element from the y array? So there is a, I mean, command for that. So you have to write find. Okay, so let me check what is the command. I have write down. Yeah. So you have to write down find an x array, and when this x array will be equal to x1. So whenever this, I mean, it will look for it will look in the x array, and when this x1, I mean, which is 2 here. So when it will find the element 2, so the so it will search from the start. So it will check with the initial one, which is 1, and 1 is not equal to 2, so it will not give the output. So whenever it will match, it will give you the index. So index, let me write down as index 1, and what should be the output if I run it? So it should give me number 3. So in index 1, number 3 should be stored. So let me check it. Yeah, so you can see that it is giving me the index where the x1 is stored in x array. Similarly, you can find the index of this x2 also. So for that, you have to write down this command, and let me run it. Yeah. So now we know what are the index for this x1 and y1, for x1 and x2 in our x array. So once we are done with our index, then you can extract the y values. So y1 should be uh, what? So it should be y array, and here you have to write index 1. So if I run it, it should give me the third element from the y array, which is 2. So yeah, so this is our third element, and you can see y1, it is exactly giving me this value. So in this way, you can also extract what is y2. Now if I run it, then we know what is the x1 value, x1 y1 and x2 y2. So I mean, now the code is generalized. I mean, you can change anything. So here you can write any other number also, and from the for that it will give you what is the y x1 y1 and x2 y2 values, and it will give you also the index. So I mean, 9.2. So it is around the last in the last range. So it is showing what are the index of 17 and 18, and it is giving you x1 y1 x2 y2. So once you get this, so you can calculate the slope. So for slope, what should be the equation? So it is y2 minus y1 divided by x2 minus x1. So in this way you will get your slope, and once you get your slope, so then what is the equation? So the value will be equal to y1. So what is the value? So this is a slope. So y1 plus slope into x minus x1. So y1, we have our slope into, so what is your x? So you want to find that xm. So you have to write down here xm minus x1. Now if I run it, and let me just suppress these outputs now, and I want to now compare this ym interpolate and this ym, does they match or not? So I mean they should match, because this is how MATLAB does. MATLAB interpolation function, which and the linear one, this is done exactly in same way this works. Maybe, yeah, you can see that it exactly matches. So I mean you can change this numbers, you can make this more dense points, and you can see that it is matching. So exactly this is how this linear interpolation works in MATLAB. So now here, instead of this one point, I mean you can give it as an array. So xm is suppose 9.2. Then I mean for array, so how we will write it? So suppose you want to know at this values 1.25, 3.5, 6.24. Okay, so let me, because these points should will be present, so make it different, 1.2. Okay, and for now let me just comment it out, because it will give me error because it is already an array. So so now if I run it, so what should it give? It should give the y array. So this interpolation inbuilt function, so I mean it works with one scalar variable, or you can, I mean in with one single command you can extract the x values for all of this. You can extract the y value for each of these xm values. Now we can implement that in our code also. So how can we do that? So let me try to do it. So what you will now check. So let me write down this an xm array, and you have to write down your xm array. And so for, so I mean, so you have to run a loop, because you want to do the same task now for all of these values. So you have to write down for loop here. So for xm equal to xm array. So xm will take the values from this array, and it will do this. So and I mean I can create an array also. So ym, which is, let me create an zeros, and row 1 and column should be, it should be equal to the length of xm array. So this is our ym. Uh, okay. So if this is our then what should we do? We should store this. So okay, so let me define it in this way. Now you want to append this ym value. So for that you have to write down this ym array and you want to append the ym value. So now if you do this and hit end, and after the append I will just want to show, I just want to see what is the ym array. So after the loop I can print the ym, what the ym array is. And so now let me check with this. So for each of this number I should get, so now you can see that here also we have defined the we have make the for loop. So now what it so how it will work. So I mean now this code will work for a uh, for array also. I mean you can give other number also. I mean you can increase the the data set, and this will do you the task of interpolation for yourself. So now you can write this as a function also. So how you can write this as a function. So whenever you want, I mean, we have learned how. So whenever you want to define a function, so first you have to tell MATLAB what is the function, and after that you have to write what is the output of your function. Then you have to give a name to your function. So I mean, I will give it name interp1 on. So this is, I mean, we are defining the function, and here so you have to give the inputs. So what should be our input? So I should give this. So there should be two input. One will be our x, and one will be, okay. So just let me write down is an x array. So this is our x input, the function, and then we have our y input. So if I just give this two input, and does it need anything? So I mean, whenever you are defining a function, so the variables that you have declared outside, so it doesn't pass into the function. So you have to, so I mean, when it will go in the function, when it will execute in the function, so it will search for this xm. So also you have to give the xm also the uh, input. So you have to write down this xm array. So this is your input in the function, and then so let me check this out. This is your x array. These are the inputs that you are giving to the function, and what should be the output. So output is our ym array. So just let me write down here ym array. So maybe this is working. This will work fine now. Okay, so I can define it here, because now that should go inside the function. We are telling here xm array giving. Okay, so this is xm array interpolated. Now you write down. Now you have to call the function inside the script. So inter p1 own. So this is our x array, y array. This is the xm we are giving, and I mean this right now we don't need to write, because these are the inputs that you should give to the function, and this is the output, the output of the function, which is this ym array that will be stored in this variable. So ym interpolated code. I mean, so this one will be stored here. So let me just run it. Okay, so now we can see that we have created a function. So now what you can do, I mean, instead of writing it here, I mean, you can. So if you are dealing with a very large code, so suppose you are doing very complex task and you have to write multiple functions for that. So I mean, if you write all of them in a single script, so it will be very lengthy, and it will be very so whenever you are tracking something, so I mean you may have some error in your code. So when you want to find where the error is, so that may be cumbersome or tedious. So what you can do, so you can once you are sure that the function is working, so you can save it as another script. So let me just and you can save, so let me save it as another script. So whenever you're saving in another script, so you have to make sure that it is saved in the same folder, and the name now should be the name of the function. So I mean you cannot change the name now, so here you cannot write something else. So uh, I mean anything you cannot write, because you have to save it as the name of the function which you have created. So let me save it. Okay, and now let me clear everything. So you have so I mean now here you can change this array also. I mean you don't need to. So let me show you that this works even without, I mean even if I change variable name here. So this is x, this is your xm. Okay, so now let me run it. So first it will clear everything, and now we can see that it is still working. So what it will, so how MATLAB will work now? So first it will, I mean this is an inbuilt function, so MATLAB knows what it is. It will give you the values corresponding to ym. Then it will look for any function, I mean so interp on one, so that is not an inbuilt function. So it will look if it is present inside in this script. So I mean in this script there is the function is not present. So it will look now in the folder where in which you have saved this script. So linear interpolation on, this is saved in this folder. So it will look if there is any function which you have saved under this name. So I mean, so here you can see that this is a function, and you can see that there is this change of in the symbol. So this is script, but this you have saved as a function. So if I open it, so I mean, so this is your function which you have created. So I mean, if you run it, it will not run, because it will show, it will give you error because not enough input argument, because this is the function and this is the script. So now if I run it, I mean we can change this number. So let me change. Okay, so this is working. So this is how a linear interpolation work, and this is how, I mean, with the simple logic, you can create your own function. You can, I mean, make your look script very clean. So there is, I mean, you. So here you have defined this function. So and I mean, we can see the power of coding. I mean, we can see that these values are exactly matching. So this is how the inter any function, I mean is saved in MATLAB. So whenever there is an inbuilt function in MATLAB, always keep in mind that that is, I mean, function which is already inbuilt, I mean it's pre-written in MATLAB and it knows how it is. So you can create your own also, and you can save them as a function. You can call. So I mean you can go to now. What is the advantage of saving it as a script in the same folder? I mean in the same folder you can go to any other uh, script, and there you can also use the function, so that interpolate one own. So you can call it here also and it will execute. So I mean you can call the same function in multiple codes in inside the same folder. So this is how your linear interpolation will work. Okay, so there are other kinds of interpolation method also. So for example, so let me go here. I mean, you can now play with different kinds of function, different kinds of uh, data point, and so on. So, so after linear interpolation, so there is another interpolation method, which is, I mean, fitting a polynomial. So here what you do, so I mean, if you have large number of data point, so you want to fit a polynomial of that order. So if so from this polynomial fitting, I mean, so you can so instead of looking for this nearest neighbor point, so you try to, I mean, so MATLAB will, if you use the polynomial, it will try to find a polynomial so equation that will fit all the points, and from the fitting, so it will give you the output. So I mean, so and that is not also a good way to look at. So for example, if you have if so if you have 100 data points present, so suppose you have 100 data points, then MATLAB will try to fit a polynomial of order 100. But fitting a polynomial of order 100, so x to the power 100, so I mean you have this 100 coefficient, and fitting 100 coefficients to a data set is very time consuming and also computationally expensive. So that is why, I mean, this works for a very small limited number of data set. But if you have a large data set, I mean, whenever you are having an also experiment data, so whenever, I mean, there should be a large number of data set. I mean, and also, I mean, maybe there are cases when you are dealing with millions of data points, and from that you want to find, I mean, you want to use interpolated, you want to know what is the interpolated value at a particular x value. So fitting a polynomial of that order, I mean, it's too much time consuming and computationally expensive. So that is why it is not a proper good way of fitting. So another kind of fitting function is spline fitting, and I mean, this is the most used fitting interpolated function. So here how it works. So instead of fitting, now here also you will search this linear point, I mean nearest neighbor point. So if you want to know what is the what is the value at this point, so in the same manner you will look for what is the nearest neighbor point in this direction and what is the nearest neighbor point in this direction. But instead of fitting only a linear function, so in the linear function, I mean, so because in the linear function you don't have any parameter now. So once you know these 2 points, I mean, you so there is not any other parameter which you can play with. But now if you fit instead of linear, if you fit a polynomial, so in spline what you are doing, so I mean, if this is your data point, so and you want to know at this, so this is your xm, so this is your x1 y1, and this is your x2 y2. So instead of fitting linear, so whenever you are fitting the linear, you don't have any other parameter to play with. But if you suppose fit a polynomial of order 2, so I mean then and then you have the parameter to play with. Then you can fit a polynomial of order 3, order 4. So if you increase the order of polynomial, so it will give you a good fit. So that is why spline is, I mean, mostly used, and order 3 or 4 is almost sufficient for a good enough data. So and also what then now what is the so in spline also you are fitting a polynomial, and in, I mean, in the in the last case which you have which I have stated, which is the polynomial fitting for the overall data set. So there also we are fitting the polynomial, but the difference is that in the previous case we are not looking for the nearest neighbor data. I mean, we are looking all the data sets. We are looking at all the data that are present, and we want to fit a single line. I mean, single polynomial fitting. So that will, I mean, fit the all the data points. So we are not working with the nearest neighbor data. We are working with all the data, and that is why we need larger order of polynomial to fit. So that is why it was computationally expensive. But here, since you are working with only the nearest neighbor point, so you are working with two data points. So order of 2, 3, that order of 3 or 4, that seems to be, I mean, that is good enough to get the fitting. So let me give show you how you can do the use the spline fitting in MATLAB. So for spline fitting, you have to, I mean, so the this function will be same because you are doing the interpolation, but instead of linear, you have to write down spline. So here, so this is your spline method, and let me give it a different name, SPLIN, and let me for now let me make the dataset small to show you something. And these are the points which I want to know. Okay, so now let me run it. Okay, now we can see that this is from the linear inbuilt linear function. Okay, so I mean you can define order here. So maybe third order, it should not maybe go inside the, yeah. So this is put it here. Okay, so we can see that this is our interpolated value using the MATLAB inbuilt linear function, and this is the interpolated value which from our own created interpolation function, linear interpolation function. But now if you look at the spline, we can see that the values are I mean there is a large difference in the value. So I mean this is 0.08, this is 0.44, this is 13.48, 13.64, this is 39.22 and 39.02. Now if you reduce the spacing between data point, then you will see that these values will almost converge. So let me make it 0.5, and now we can see that the difference has now been reduced. So now we can make it much more smaller, 0.25. So you can see that it is almost now almost close to each other. So you can make this much smaller. So maybe 1. Okay, so this will not exactly fall with any data set. Fine. So now let me run it. So you can see that it is almost approaching to each other. So let me make it 0.05. Yeah, so 0.025 maybe. Yeah, so we can see that as we keep on decreasing the step size between data points, so there is this this linear interpolation. It almost is a good approximation to the spline fitting. So the linear one, linear is computationally less expensive than spline because in case of spline you are fitting a polynomial. So you are so that is why it is computationally expensive. So if you have a good enough data set, so I mean, so here you can, if you look at, so it has 361 data points. So I mean, if you have large enough data point and you want to know interpolated value at a certain point, then I mean, if you are dealing with larger data points, then almost the linear linear interpolation and spline interpolation, they almost give you the exact around same number. So if I mean, if you want to I mean, if your priority is to I mean, if you if your priority is to use less computational power, then you can go with linear. But if you want to know the, I mean, if you want to approximate the best, I mean more close to the actual data, then you can use the interpolation spline. So I mean, now let me look at what will be the exact now value of in x. So what are the data points in x? So okay, this is, so for example 1.05. So if I write down here 1.05, so what will happen? Let me check. I mean, right now, I mean, if I run it, so it will match with the exact number. So it will give us the third value in the y array, which is point minus 0.6323. So let me check if it is the case. You can see that it is giving me the exact value, but here we can see from our defined function that it is not exactly the same. So the issue is because you are looking whenever it is exactly I mean greater than 0 or less than 0. So our defined function, so you always, you are, I mean, you are not checking if it is matching with the exact number. You are just checking if you are just taking the point which is smaller than that or larger than that. So that is why, I mean, you, so it is giving us a different result. So you can try to think how you can make the correction in this defined function, and you can try to think how it will exactly match with the interpolated value. Okay, so let me go back to our original, what is it? So this is, it will give us this value. Now let me check what is the exact value of y at x equal to 1.21. So how you can check it? So let me just write down here that x equal to 1.21, and you have to press shift enter, and then, so let me write down here x value so that it doesn't override the what is stored right now. So and this y value should be x value, and this should be y. So from interpolation, from linear interpolation, this value is approximated to be minus 0.4068. From spline interpolation, this value is approximated to be minus 0.4071. And let me check what is the exact value of this function. So let me run it. So you can see that 4071. So it is almost exactly matching with our spline. So I mean, if we have now data point, if I make it small, then you can see that spline is almost same now, but linear one, it is deviating. So that is why, I mean, if you working with smaller number of data, so that and that is why it is advisable also to always work with this spline method. Now I can, you increase the order, so let me try to look at it. Okay, so I mean that doesn't make too much difference, but the method that you are using. So if you have small number of data points, then what is the actual value, and the method that you are using, so that value can differ. So always try to, I mean, so be cautious of that. So how, which method you want to use. So advisable is to use the spline function. So if you can afford computational power, and I mean linear and spline, so they doesn't differ too much computationally also. So it is always advisable to use spline in interpolation, and I mean order 3 4, that is good enough to give you I mean you can see from here that that is good enough to give you the result. Okay, so this is it with the interpolation. So next we will learn about uh, how you can do integration and how you can do differentiation in MATLAB. So till now we have introduced to the idea of interpolation, how you can do the interpolation. So next I will discuss two fundamental things. So one is differentiation and another one is integration. So I mean how do you define differentiation? So if so let us again go to the fundamental or basics. So what is differentiation? So suppose you have your so for example you want to have the differentiation of, for example, this is a function and you want to know what is the differentiation. So okay, so how the differentiation is defined? So you have your x array. So you have certain points in the x-axis, and for each of the value of x, so you will have some value of your function. So it can be simple like this, or it can be very complicated, sin x plus I mean by to the power x minus 1. So it can be very complicated, it can be very simple, but the point is that for each x point you will have some value of y. So you will have your fx values. These are your y values. Now when you want to get the differentiation, so the uh, definition of differentiation is that, so so y n minus y n minus 1 divided by x n by x n minus 1. And what is another important thing? So so the this x n minus x minus n n minus 1. So this x point, so let me call this as h. So the difference between our x data point. So there should the limit of h should be tends to 0. So so how can you implement this in your code? So in your code, so you will have this x array. So these are your points, and the difference between these points. So it can be uniform. You can make it generally. You will take it as uniform, and this difference it should be tends to 0. You have to take the step size very small. So how small? So that you have to understand from your code. So I will show you how you can choose this. And so what is this n point? So n is so you will start from here. So if you want to find, so this you have some certain y value here and you have some certain y value here. So you will, this is your, for n equal to 1, so this is your y n. So you will start from 2. So at this point, if you want to calculate the differentiation, so you will minus, so you will write this yn minus yn minus 1 divided by this uh, differentiation between this point, which is h. So how far will you go? So you will start from here and you will go up to the end point. So there is one point that will be missing. So because you are, so if you start, so for example y has your length. So for example you have 10 points. So how you will get the first point? So you will make y2 minus y1. Then you will for second, and you will store, so you will get 1 point here. So let me call it diff1. So this is your first point in your differentiation. So then you will calculate y3 minus y2, which will be your second point. Then y4 minus y3, and this will be your third point. And in this way, what will be your ninth point? So ninth point will be y10 minus y9. So you will till this you will have 9 data points. Now, if we want to calculate the 10th data point, then you have to go to y11, so which doesn't exist in your array.
So that is why you will have one less number of data point in your y array, in your array, in your differentiation array. So there is an inbuilt command in MATLAB by which you can calculate the differentiation, and also there is, I mean, we can implement this the very fundamental definition of differentiation in MATLAB, and we can look at how I mean how that compares with our uh, inbuilt function, and also you can check if that, I mean, if the function, so if I mean so our this function or whatever the differentiation function in MATLAB is, so if that is giving the actual output which we will get or not. So let me proceed with that. First let me save the script. So lecture 4. So how we will proceed? So first we will have to define the X array. So one. So right now we will take the step size to be 1, and we will look how uh, this step size will change out, and we will have some function. So we have what the function can we take? So take some simple one. So x squared, this is the function. So this is your x array and this is your y array. So let me run it. So we can see that for each x value we will have the corresponding y value. Fine. Now we want to compute the differentiation. So how you have to do? So now you have to go through the each element in y array and do the same task repetitively. I mean yi minus yi minus 1, and that you have to do repetitively. So if you want to do repetitive task or iterative task, so for that what you do? So for that we use loop. So we can use for loop here. So for I equal to, so we'll start from 1, and how far and we will go. So what should be the, I mean, what you want to compute? So you want to compute what is this yi minus yi minus 1. So from where should I start? So if I start from 1, so it will be y1, but here it will be y0. But in MATLAB, index start from 1. So I mean, so that is why you have to start from 2 here, and you will go up to length of y. So what will be the first element? First one will be y2 minus y1, and what will be the last element? So this will be, I mean, y end minus y end minus 1, and this you want to store. So I mean, you want to store this in a different array. So let me call it diff of y. So this is the array where you will store the different value, I mean the value which you are getting after doing the differentiation, and here what you will write? So you will write basically the step size. So how can you compute the step size? So you can just write x2 minus x1. So let me just copy this and let me show you that it gives you the step size. So you can, so for example, make it 0.2, and what is x2 minus x1? So x1 will be 1 and x2 second element will be 1.2, so the difference should be the step size. You can see that it is this step size. So you can save it in h. So here you will have to write h. So here you have to give another bracket. So this is your formula, which this is the formula which you have written. So I mean this y2 minus y1 by h, and this limit condition that you have to look. I mean we will decide later that what should be the h value. For now we have set it to be 1, and then I should store it in something. So I mean, so what you can do, we can create an array and we can store it here, or we know what is the size of the array, so we can just write zeros. And what should be the, so there should be one row, and how many columns should be there? So I mean t, so sorry, length of h or y you can say, because h, x and y they both have same length, but there should be one less element because you are starting from 2 to n. So that is why this array is of, I mean, dimension which is one less. So now we can write here. So or you can, I mean, so you can write here. Should I write here I or I minus 1? Because so when I, so for the first run I will be 2, so it will execute here y2 minus y1, but that you want to store in the first element of differentiation. So you will write here I minus 1. So this is how you will store in your differentiation array. So let me close it and let me run it. Because it is just showing this output. So let me suppress it. Suppress the outputs. And it is running. Okay. So now you want to, suppose I want to see what is this diff. Let me run it. So you can see, okay, so some numbers are stored. Now, how will you verify if this is right or wrong? So one way of verifying this, I mean, you know what generally the differentiation of x bar look like. So I mean, if you so we can plot them. So for plotting, what is the command that we should do? So first we have to write down this figure number. So generally it is good to write down this. So figure 1. So here the first and we want to plot. So since we are starting, I mean we are removing. So there is one less element in the differential array. So I will start from the second one. So I mean the in x I will plot from 2 to end, and in y also I will plot from 2 to end. Then you can do the hold on, and then you want to plot. So here you will have this x which will run from 2 to end, and here you will have what is your differentiation area. So if y. So let me run it. Okay, so now if you want to see, I mean, which one is for which graph that you don't know, so you can add legend, or you can do, I mean, you can just, there is a command called pause. So you can pause. So what it will do, so here you will give second. So after plotting the first graph, it will hold on for 1 second and then it will plot the second one. So you can change it. I mean, you can pause for 5 seconds. You can pause for anything you want, but I will be I want to pause it for 1 second. And I mean, so whenever again executing the code, if you want to first, so if I run it, so basically it will update in the same figure. So if I change it, so if I run it now, then you can see that it is plotting the same figure. So suppose you want to close the figure whenever you are running the code. So for that you have to write down just this, click close all. So what are the, so I mean you have to close all, and there are these other two, clear all and CLC. I mean it is always advisable to write all these three. So let me run it. So first you will see that this graph will disappear. Okay, and then first it will So it is, pausing for 1 second. So first it will plot the first one, which is our actual function. So here, yeah. Oh, so first you have to hold on. So after this plot, it will hold on, then it will pause, then it will plot the second. Okay, fine. So now, how do you know that this is correct? So if so, and there is this inbuilt function also in MATLAB. So this is and that is generally this this function, which is diff. So there is a function called diff. So diff. So now let me check what will happen if I just write this diff y. So what it will do. So this is our difference array which we are creating from our written code, and let us come to this diff y. So you can see that it is the same. So this diff function in MATLAB it basically does the same thing. It if you give an array to it as input, so it will uh, just it will give you output. In output it will give you another array. So,
So in output, it will give you another array where you will have one less element. So let me store it in something called D. And so let me just execute it. So you can see that this D, this has dimension 1 is to 9, and our Y has dimension 1 is to 10. So what we are creating from our code, so which is exactly similar to this D array. So this inbuilt function basically does the same thing. So it runs for this loop for the length of this array, and it just stores the difference values. So now it is storing the difference. So similarly, you can have the difference in the x also. So for that, you have to write diff x. So if you write this, so it will give you a similar array in y axis, is in x axis also. So let me show you that. You can see that the difference is uniform. So it is giving all the elements are 1, and there should be 9 elements. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 elements, and it is giving me the difference array. So let me give it a different name. So diff y inbuilt, because it is inbuilt in MATLAB. So I'll just write down this way. And you want to plot. So you want to just pause initially again, maybe for 1 second, and you can write here inbuilt. Fine. So let me plot it. So it will close everything. It will clear the workspace. Okay. So you want to compute the element wise operation. So I have done mistake, so here you have to put this element wise operation. So otherwise it is just giving you the one scalar value. It is just doing traditional matrix division, and it will give you a value. But if you want to do element wise, you have to give this dot. So that is why it is important to remember it. So now, okay, so now you can see that it is giving the actual array. So this is okay. So this different this inbuilt function and our defined function, so they are good to go. But how can we check if it is okay or not? So this is our original function, and we know there exists a special function. So if you make derivative of it, it will give you same result. So we know e to the power x. So if you make differentiation, it just basically gives you e to the power x. So you can check with this function if it is right or not. So here, instead of x cube, I will just write e to the power x and let me run it. Okay, so it is not matching. So this is our defined function, but this is what the derivative is giving, but actually it should coincide with it. So remember, there is another condition. This h tends to be 0. I mean, you have to find this limit properly. So let us try that. So let me try to make it 0.8 and let me remove it for now so that you can see how it is being updated in the same graph. So run. Okay, so a little bit good. Make it 0.6. Better. Make it 0.3. More better. Make it 0.1. Almost matching. So let me remove this close all now and let me check the result. It will delete this. Okay, so there seems to be almost matching. If you make it more close data point, now it is almost indistinguishable. So you can check with this. So I mean you can make the plots look more beautiful. So you can put label and then you will have your y-axis, y label. So if I run it, so the label will be updated now. Yeah. And I mean you can so make the properties different. So line, you can make the line with more bold. So you can make it 2 for each of them. And for I mean you can put different style to look at. So line style, so maybe something like this. So I mean the dotted one is the I mean inbuilt function. So here also you can give different line style. So you can put O here maybe. Okay, so diamond, I mean that should work maybe. So we'll I mean we have used this in the previous class, so you can look from it. So maybe this command is wrong. Line style diamond you cannot write here. So just look for it and update it. But this is the idea. So this is how you can I mean distinguishable. You can distinguish between the plot and remove this. Okay, so we know that these two are giving the same result. So right now I will just uh, comment it out, and here I will put this line style, and I will just I mean I will just comment the pause also. So yeah, so this is how I mean. So now we are convinced that the step size that we are using, so that is good enough to give us the actual result, because we know that the derivative of exponential should be exponential. So it is matching with the step size. So I mean we can try with different function. So if we have x, So derivative of x should give us a constant value. So it should be a constant like curve. The derivative one should be. So you can see that it is giving me a constant value, and you can play with different kinds of functions. So e to the power minus x, you can have sine here, and you can add an offset. You can plus, you can have here some x cube kind of thing, and you have to have the dot dot. So remember that. So let me run it. And yeah, so this is our actual function which looks like, and this is how the differentiation will look like. So this is how you can use the inbuilt command, so that will give you the result, and this is how you will write this inbuilt command works. So you can use your own differentiation function, and you can give any function as an input, and you can look at so once you are pretty convinced that the step size is good enough, then you can play with different kinds of function to look. So and also let me mention another thing. So the different so what this is the first order differentiation, so first order derivative. Now suppose you want to have the derivative up to second order. So for that, what you have to do? So if you want to write your own command, then you have to create another loop. So in that loop you will run from I from 3 to length, because then it will be your y array, this diff array, it will be your new array, and from that array you will run this again. So you can try to write down that code in your own. So uh, you can create a function. So it is good, it will be better if you create a function and you call that function multiple time, and you calculate the differentiation of it. So since we are, you can try to do the, you can try to write your own differentiation second order derivative function. So let me proceed with another basic thing, which is commonly used in mathematics and so on. In mathematics, whatever it is. So it is, you will always encounter with this integration. So basically, what is integration? So integration is basically nothing but, so if you have this, so it is basically summation, but and differentiation is basically division. You are doing subtraction. And here in integration, so you are doing summation. For example, if you have a data set, so these are your data point, and suppose you want to integrate. So how you will in it? So basically, what is the formula for integration? So if you have a function, so f of x dx, f of x is your function, and you want to integrate. So for example, so then what do you know? So you will have some different function of x. So if you have this limit, then you will have a number, or if you don't have the limit, then you will have a function of x. This function will be different. So for example, if you want to integrate x dx, we will get this x square by 2, and there will be integration constant. So the integration constant, so now if you want to write the code in MATLAB, so how you can do? So basically integration is, you have the x array for in your code. So so for example, x is 0 1 0 1 2 3. So this is your integration. So this is your number in the x array, and for these numbers you want to calculate how the integration will look like. So, if you have this x curve, so your integration, so if the constant is 0, then at x equal to 0 it will be 0, and it will match. So where it will match? So when this will be same, so x will curve which match at 0 and 2. So if this is 2, so your integrated function will also look something like this. So how to plot this and how to get this function from this data? So so if you can generalize, then you can do with any kind of function, and you can look at the indicated value of it. So the idea is that if you have the points in the x-axis, so for example, this is suppose xi, and this is xi plus 1, and this is for xi you will have the yi here, and here you will have yi plus 1. So we will go with the trapezoidal rule. So what is the trapezoidal rule? So in trapezoidal rule, you have to calculate the, so what will be the value at the midpoint. So if you want to know what is the value of this integrated function at x equal to I plus 1 at this x value, then what you will have to do? So you will have the yi value, and you will add this. So so this is your integrated function, so maybe write it as capital Y. So yi, and then you will do? So yi plus 1 plus yi divided by 2. So it will, you will take this value here, the value of the previous one and the value of the next one, and divide by 2. Then you will multiply with dx, because if you want to integrate this, so basically the idea is that you will write x. So one thing you can do, xi into dx, and you can some summation over I. Or another thing what you can do, so this is the easiest thing, and in trapezoidal rule what you will do, so you will basically add this xi plus 1 plus xi by 2, and you will multiply this with dx. So this is your function. So how your function will look like at I plus 1 and I, you will divide this by 2, and then you will multiply it with dx. So let me show you how you can write this in MATLAB. So let me open another script. Let me save it as lecture 4 integration on. Let me clear all first. Now first you will define your X array. So one is your X array, and let me take a function, simplest function x, and we know that its integration should be x square by 2. So at x equal to 10, your the function of the integrated value should be 50. The value of the integrated function should be 50. So now what you will do? So you have to again, do the same task iteratively. So you have to define, you have to write a for loop. So for 1 to length of y. So what you want to calculate? So you will so integrated y. So we have this integrated array. So which you will save it as zeros, 1, and it should be the length of y. Then for this range, you will write down this. So we will check if this should be I equal to 1 to length y or not. So and the integrated values we want to store in y. So int y ith element, and what should be this? So it should be int y I minus 1. So effectively it should start from 2, because the second value will be the first one, the first one plus, and then what you will do, you will here you will write down the values of this y. So y So you are calculating at I, what will be the value at I. So you will write I, because you have to write down the function here. So I minus 1, and that should be divided by 2, and the whole thing you will multiply with dx. So what is this dx? So dx is basically the step size, and let me end it. Let me show you how the integrated array would look like. Because you can see that we have this integrated y array. Okay, so this is how you will do the integration here. So let me plot them together. So how to plot? So I mean, if you look at the dimension of them, so the integration array as the and this y array x array, so they both have same dimension, but where we are taking care of the constant. So whenever you will do integration, so I mean you will have this as a result of, if you don't define the limit, so you will generally end up with a constant. But where is this constant? So basically, if you put x equal to 0, so for the first value, you will have the constant. So that constant value you can add as an offset. So how you can do? So if you want the constant to be 2, so you can add it 2 here, or if you want the constant to be, I mean, something different, 1, so that constant also you can add here. So in this way you will define the constant. So after you get this integration error, so you can integrated array, so you can just plot it. So let me write down figure. So plot, here you will have the x, then you will have your y array, then you will have, I mean, you want to plot both, so you will have, hold on, then you will plot x, and with x what you want to plot? You want to plot the integrated array. So this is your integrated array, and maybe line style you can do different. So line style, maybe you can do this, run it. Okay, so you can see that it is almost giving me the exact result, because it will starting from 0, so at x equal to at y equal to 1, I mean x equal to 1, y equal to 1, and for the integrated array also x equal to 1, y equal to 1, and then I mean it is giving us the integrated value. So I mean you can uh, play with different kinds of function. So x, you can try with exponential. So we know that in case of exponential, I mean, so it will match. So as you can see that I mean, so exponential. So and this is how the original function look like, and this is the integrated function of this exponential. So both of them are almost matching. This is how, I mean, this is the basic thing how you can implement the integration and differentiation in MATLAB. So you can try to play with them. So you can try with different kinds of function and how to do that. So in the in the next class I will introduce I will tell you how to solve differential equation. So for example, if we have a first order differential equation, for example dy dx equal to fx, and also we can have second order differential equation also, so I mean a different function. And so you will have a initial condition. So here you will have one initial condition, here you will have two initial condition, and there is, I mean, you can use different kinds of method to solve this kind of differential equation. And how to, I mean, you can also plot them. So I mean, in the next lecture, so we'll explore how to solve this differential equation, because ultimately we want to explore different kinds of harmonic oscillative equation. So if you have this, this is the basic harmonic oscillative equation we know. So this is the second order differential equation, and if so this is how the solution will look like. So we will try to, so in the next class we will solve it from scratch, and also we will introduce damping to it, and also we will look at how the oscillation should look like. So it will, for damping it should basically slow down. We will explore that in the next class. So that is it for today. So today we have learned about how to or what is interpolation, how you can do interpolation using MATLAB inbuilt function, and also write your own function. Then we have to explore the integration and differentiation. And next day we will solve this higher order differentiation equation.